right, so we're gonna look at those two discussion questions there. So the first one, why do tightrope walkers use long poles or hold their arms out to the side when they walk that tightrope? So the idea here is I don't want to tip over as fast. So the goal is I want to minimize this alpha value. Don't want to accelerate and tip over. Now the nice thing is that I'm straight up and down, mg produces no torque because it's not perpendicular. And as I tip a little bit, then mg starts to have a component that is perpendicular. So if I can at least stay upright, then it's easier to stay balanced. But as soon as I tip a little bit, well, then that mg starts to apply torque to me to knock me over. So what's the idea with the arms out? Well, the arms out is thinking about that moment of inertia. If I lift my arms up, I've moved that mass further away from that axis of rotation, I'm going to tip over slower, so I'm going to have more time to react. But you might say, yeah, but you're increasing your center of mass height. So you're increasing the R value. So gravity's going to have more torque. So how can you have it so that it produces more torque, but it has a lower alpha? Which one wins out? And what we want to focus on here is the torque is proportional to R, but the moment of inertia is proportional to R squared. So by increasing that moment of inertia, you're increasing that overall I value more than you're increasing the torque, and so you get a net result of a lower alpha value. Now why switch to the pole? And you'll notice when they hold the pole, they usually hold the pole like at their waist. And the idea there is we don't increase that torque. If anything, we lower that torque and increase I. So we get the double benefit there. The second one, why is a tapered water glass with a narrow base easier to tip over than one with straight sides? So I have my narrow base here, and if I give it a little tip, it's not very easy to tip over. That's because it's got water in it, okay? But the idea is that if you ever get a situation where mg vector is outside of your base, the object's going to tip over. And so you can even try this at home. If you try to get your center of mass, which is essentially your belly button, outside of where your feet are standing, you're going to have a hard time standing up. You're going to tip over. And so the idea is that as long as that center of mass is above the base of that cup, it's not going to tip over. And so if I get that water in the bottom, it's actually very stable because that center of mass is very low here. So it's hard, I'd have to tip it a very long way to get it over that edge of that base. But if I fill that cup up more, that center of mass gets higher, and so that tip is going to get that center of mass over that edge a little easier. So a full glass is a little easier to tip over, meaning it doesn't have to tip as far before it tips over, than a nearly empty glass of water. Okay? Now this brings about an idea of stability, that the same glass is easier to tip over. So for instance, if I take this meter stick, the center of mass is right here at the center, and I let it go, it tips over. But if I hold it at the top, it doesn't tip over. So if your point of support is above your center of mass, where your weight is, this is called a stable situation, meaning that if it kind of starts to tip, it goes back to being stable. Where if I support it below that, if it starts to tip, it's unstable. It won't come back. And so this kind of brings up this idea when we go to the amusement park, well, the water park, let's be honest, and they have those big buckets, and those big buckets tip. And how do they get them to tip? Because that's a lot of weight to actually mechanically tip it. So what they actually do is they give it a support point. Okay, and so this is the support point of the bucket, and it starts out with a small amount of water or no water at all, and the center of mass is here, meaning it's a stable situation. But as I fill that water up, that center of mass goes down a little bit when it's not very full, and then as I fill it up more and more, that center of mass starts to creep up more and more, okay, until my center of mass gets above, that's the support point, and then it tips. And so here, I've actually made one. So let's take a closer look at this. All right, so we've kind of narrowed in here. So I built this one here just out of curiosity. And so at the bottom, I kind of made a V shape. And the idea there is I'm going to essentially have some air pockets built in. And the idea there is that my center of mass is going to go up higher than the halfway mark when I start to fill this with water. And this was brought about by exactly that big bucket that I saw at the lodge at Cedar Creek when I took my kids. So let's see how this works, because right now it has a stable situation, but you see how easily it swings back and forth? That means that center of mass is pretty close, because the further away those two are, the less swing you get. And so as I start to fill it up, you'll see when I first put that water in, we get that stability. It's more stable then, okay? And so as we start to fill it up more and more, we should get to a point where it actually is going to become unstable. And it will eventually tip. Whoop. There we go. So the idea there is that that center of mass moved above that stability point, and that was what caused the tip, not so much that the moment of inertia was changing. It was more of a stability point problem there.